we learned from our newer studies that it really makes sense to look to the different modeling approaches and run them through non-MEM or any other statistical package that you use. And you will see that there are differences. Now, so it's important to understand these models. Before trying to understand these models, you have to understand the formula of the basic concentration versus response relationship, as I showed you. But the Emax model that I showed you only works for one drug. If you want to study the interaction of two drugs, these two sigmoidal curves has to be normalized. Otherwise, the cubic design of the surface is not possible. So you have to normalize the potency of these two drugs to each other. The best way to do that is to normalize them towards the effect site concentration of 50%, the EC50. And this is done in all the surface modeling approaches that I will explain to you. So that U is the normalized effect site concentration of a specific drug. And that's the formula of the effect site concentration, a specific effect site concentration of that drug divided by its EC50 in that population that you're studying. So the probability of having a specific response is the combination of that specific potency powered by the gamma, the slope of the curve, divided by 1 plus that U gamma. So this is the basic formula to give you an idea of the potency of one drug or multiple drugs. The gamma is, of course, the slope of the sigmoidal function. If you represent the interaction in such a way, you can combine the potency of various drug combination into a two-dimensional plot, as we did here in the anesthesiology paper we published. So, for example, this is the combined potency for tolerance to shake and shout when combining propofol and sevoflurane. This is the potency of a tolerance to a tetanic stimulus. You see that you need more drug, or the combination of the two drugs, to have a tolerance to laryngoscopy, and even more, this is LMA insertion, sorry, and the tolerance to laryngoscopy. So it's a powerful tool to combine or to show the interaction of two drugs on a two-dimensional plot. And this was done previously by the Utah group in one of the first prototypes of what later would become the G Navigator. Here you see the way of their representation of the two-dimensional combination of that U. So all the models that I will describe, the Greco, reduced Greco, Minto, and the hierarchical models, are just another way of representing that U in their combined drug administration methodology. So the Greco model, the first one, gives you an idea of the total effect that U evoked by two drugs A and B. The Greco model is the sum of the effect of one drug A plus the drug B plus a potential effect of the combination of the two drugs. If there is no additional effect, then your alpha term will be 0. And then, of course, you have just an additivity. If it's something different than 0, you will have a superadditivity or an infraadditivity. This is the classical Greco model. Now, there are a lot of limitations to that Greco approach, because the two drugs should have a maximum effect. And that's sometimes a problem when we are studying hypnotic opiate interactions, because, for example, opiates alone are not able to guarantee anesthesia. So they don't have a maximal effect if you look to loss of consciousness. So only one alpha factor is estimated also in the Greco model. Only one alpha is estimated for the totally 3D response surface. That means that the shape of your interaction on the surface is always the same. If you're looking to 5, 50, or 95%, this is not giving you a lot of flexibility. So it's little flexibility if you want to model more complex interactions between two or more drugs. So if you have a drug like an opiate, you have to modify your Greco model. And this was done in the literature. It's called the reduced Greco model, where in fact when you have a drug B that doesn't evoke a maximal effect, for example, an opiate, then that opiate, which is drug B here, only affects the interaction factor alpha, but it should just be left out of the formula. So then the reduced Greco model gets an approach where the A drug is the drug of importance, and the B drug is only affecting the interaction factor alpha. And the effect, the added effect of your second drug becomes neglectable here. There are also some assumption and limitations to that reduced Greco model, because drug B acts by adapting the potency of drug A rather than by expressing its own effect, as I said. So the Emax is only determined by your first drug, and only one alpha factor that stays the same as with the Greco model. It's just one alpha factor for the complete surface, and as a result, you still have little flexibility. This was understood very well by Charles Minto and the Stanford group, and therefore Charles, studying also the interactions of opiates and hypnotics, wanted to add more effect, more complexity to their modeling. So they said, well, let's try to build another model where each combination of the two drugs is quite independent from where you are on the surface. So it's an independent concentration response relationship, as if it was created or evoked by a new drug C that has an independent effect on CE50 and gamma. As a result, the CE50 and the gamma of that new drug C are in relationship to the respective amount of drug A and B administered, and are allowed to be flexible according to a complex quadratic function. So theoretically, one combination of A and B can be at a certain moment synergistic while being additive or infra-additive at another point in time. They add that flexibility by introducing a theta term in their formula, which gives you a better idea of the interaction at each level. As a result, they also needed to add more complexity to their model, allowing more flexibility in the modeling surface. They did that, and I will not go into details in that, by adding a more complex total gamma term. The slope of the surface is the linear interpolation between the slopes of the various drugs and another interaction term being the beta, which is a dimensionless interaction term, giving you an idea of that interaction. They also have, for their U50 calculation, quite a complex quadratic situation here, quadratic function of theta. And why quadratic? Because the group thought at that time that offered enough freedom to cover all the complexity in the modeling work. So you see it becomes more complex and complex. And this is their total model, where you see that this is the gamma, which is this one, and the U50, which is that also quadratic complex interaction term being a function of theta. But it still goes back to our basic formula. You see clearly here the same U and P combination coming back, and of course these are the other terms you need to build your sigmoidal shaped curves. This is the Minto model, more complexity. The big problem, and that's what is in many words on this slide, the big problem of the Minto model is that it will also wants you to show some synergistic interaction. So you have a kind of a bulging effect in your model. which might sometimes result in some problems while you're modeling. Next to this, Thomas Bouillon and co-workers had another idea based on what I don't remember the name now, an editorial in anesthesiology was written on the two universa of anesthesia. You have the hypnotic component and you have the analgesic component. So that's not one universum. It's two universa that are combined during anesthesia. First, you should start with your opiate, because when you give a stimulus to your patient, that's pain in, your first drug will try to avoid the pain increasing or going up to your cerebral cortex, influencing your final output, your consciousness. So you put a patient to sleep with your hypnotic drug. If you hurt the patient, the noxious stimulus, the patient will arouse. That's something we all know. So to avoid that the patient arouses, you have to give an opiate to block the arousal reaction. So first you need opiate. And when you give an amount of opiate, your projected pain will decrease in relationship to the amount of opiate that you give. As a result, your hypnotic level will be influenced by the pain stimulus that is projected on the hypnotic part. And the total result will be your response or tolerance to responsiveness on your consciousness level. So this is the hierarchical model by Bouillon and co-workers. I will skip the mathematics for you because I think you had formulas enough. But just to give you an idea, it's just the combination of what I draw in the figure being the combination of the post-opiate intensity, that's the first step, being the pre-op intensity plus a concentration term describing the potency of your opiate. That's your first step. And of course, then you need to go to the next level, being your second part of your model, and that's resulting in the final model. This is your post-opiate step, and this is your final model, describing the relationship of pain in step 1, step 2, and your consciousness out. Okay, so this is the model how you do that. And we're still going back to our first P formula. This is our final model, and you can replace this formula by the concentration relationship. Now, this was published in anesthesiology, and then later on Thomas Bouillon realized that there was a overparameterization of his original hierarchical model with a lot of slope factors. He deleted that overparameterization component, published a chapter in a book on that, and we tried it, and we proved, in fact, that the original hierarchical model as published in literature was really overparameterized. So now in the final model that you will find in devices like Smart Pilot View, this system uses the modified hierarchical model with less parameters than the original described model in literature. Well, we are back to where we started, because in fact, the modified Bouillon model is quite close to the original Greco model. So does it make any difference what we are doing? Well, let me give you an example. This is a study we recently published in anesthesiology from Bjorn Heisen and co-workers from our group. Sevoflurane remifentanil interaction, crisscross protocol. Forget about this. We compared all the models in a dichotomous data set. Reduced Greco, Minto, and two different hierarchical models with a fixed opiate or an open opiate effect. These are the surface models, and I will give you some idea about the differences of the models. This is the Greco, the Minto, the hierarchical, and the modified hierarchical model for the isobalts representing a probability of having tolerance to laryngeal mask insertion at the 5% level. Sevoflurane, remifentanil. Okay. Does it make a lot of difference? Honestly, I don't think so. Certainly not clinically. But we are not interested in the 5% level. We are interested in higher levels. 10%, still not interesting. I'm increasing. Okay, I'm going to a higher level. 50%. Look at here. You start seeing differences. 90%. And here it makes a difference, clinically. For the remifentanil concentration of 3%, what is my sevoflurane concentration that I will need? Well, that depends on the model you're using. If you use the Minto model, you have 1.4 volume percent entitling. If you use the hierarchical model, you will have 0.9. Now, I think that 0.9 versus 1.4, that starts to make a clinical difference. And that's only at the 90% level. That's what happens at the 99% level, where we want to be as an anesthesiologist. You see that it makes a difference clinically. So yes, the selection of the right mathematical basis makes a difference when you want to study the interactions, and certainly when you want to apply these models into a drug interaction display as the ones that you can see here at the booth. Certainly I think that they are shown here. At least one of the companies have distributed. Yeah, Draeger has the one here, so you can show. At the 99% level, look at this. Minto, 2.4, 1.5 for the hierarchical model. Big difference. So, are there differences? Well, I say it here with many words. Yes. Does it make sense to look at all the different models when you are studying interactions? Yes, it does. But, final thoughts. When we studied our last paper by Mark Koppes and co-workers in anesthesiology, Steve Schaefer wrote an accompanying editorial. And, well, he was quite right by saying, well, at least all models are wrong, but some make sense. The differences are clinically important, so yes, it makes sense to study drug interactions, to study them in the right way, and to realize, as Steve said, that although all the models are wrong, some are useful. And although response surface models, as all models are wrong, they reduce our complex physiology to a few mathematical elements. But they are useful in clinical practice to guide drug dosing and may provide in our search for fundamental mechanisms of general anesthesia. Thank you very much. And I apologize for the hardcore mathematics.
All right, thanks a lot, Michel. Michel's going to be available also